All right. So in counting processes, the time keeps ticking from some initial time, and we keep counting. So it's a non-decreasing. Our variable xt is a non-decreasing variable that keeps increasing as we keep counting. Okay, we are not uh, uh, talking about things between two time intervals. In counting processes, we keep counting from some initial time, and therefore the variable xt is always increasing, uh, which means that which also shows that it doesn't have a steady state, right? I mean, it may go all the way to infinity, and the transition between states is transition between counts. For example, after your count become 2, it will never become 0 again. There is no subtraction. We're just counting. We're accumulating things that we observe. We're accumulating the buses that arrive. We are accumulating the scores that are scored. Uh, we're accumulating the number of successes that have happened. Therefore, they cannot be taken back, which shows you that when you get to a certain number, you can never decrease it. So the transition probability from some states, for example, if this variable becomes 6, the transition probability from 6 to 0 will all be 0 after that point. You can never go back to 0, or even you can never go back to 5 or 4 after you come to state 6. It means that there will always be 0 transition probabilities after that. So counting processes are irregular. They are not regular Markov chains. So they don't have steady state. We're not going to talk about steady state distribution of counting processes. But we will talk about things like uh, how it's related to the binomial process. We are going to talk about how it's related to our binomial distribution, and the time we wait, or the number of tries we wait until xt goes to the next state where it becomes +1. 6. When is it? How many tries you should try until xt becomes xt, not t plus 1 time. So it's what I want to show you is this. So if you're at if the value of xt is, for example, k, in which time point it's going to be k plus 1 is what I was talking about. So we are at state k currently. How many time steps have to pass until I get to k plus 1? This is actually a distribution that we already know. How many tries until first success? This is, I already have k successes. I'm right now at this point in time where I have k successes. When am I going to have a state transition to k plus 1? How many tries you have to try? If each try is in one time step, and this is like a Bernoulli try, you do it every time. How many tries until first success? What is the expected number of tries until first success? That's a geometric variable, right? So in other words, the expected time steps between two state transitions becomes a geometric variable. Uh, and the entire thing here, how many time steps have passed? For example, if each time point here is a Bernoulli trial itself, then the xt, the probability mass function of xt, the state distribution xt, becomes a binomial variable with probability with these two parameters, t and p. Yeah, h can be different values, exactly. H can be, for example, you can get to k plus 1 in h. H can be, for example, 4 in 4 steps, 5 steps, 6 steps. There's even probability in just one step you go back to k plus 1. Okay, so the expected waiting time, or any waiting time, it's a geometric variable. Since geometric variables can have values of 1 to all the way to infinity, and which means that our h value here can take values between 1 to infinity, where we make a state transition from k to k plus 1 any one of those values is possible, because that waiting time, that number of trials, is a geometric variable, which can be 1 or it could be infinity. So exactly, it's like a graph. The transitions between these different things may be represented also as a graph. But what I'm saying is that the entire if you look at this variable xt, what is the value of x in t time steps, where at every time point you're performing a Bernoulli trial, uh, and the probability of success is p. Then in t time steps you will have t trials. It will be a binomial with parameters t, p. So the expected value of xt here will be t times p, but it could have anything. So since this probability mass function will be the exact same probability mass function of a binomial with tp. Xt here can be 0, 1, 2, 3, or t. You could have exactly t successes in t tries, or 0 successes with some probability. So the probability mass function of this binomial will be this xt variable. So the counting process here that we keep track of, xt, since it's a binomial variable itself, this is called a binomial counting process if it's discrete time. If we think about continuous time, where we observe a certain number of events, for example, the average number of buses that arrive in an hour is 4.3. If I say it's 4.3, although the buses arrive one bus at a time, lambda may be a non-integer value. So lambda, if you remember Poisson distribution, we could have lambda, which is non-integer, but the Poisson process, the Poisson variable itself, is the number of things that happen in certain time. Okay, so when it becomes continuous time, it will be a Poisson process. I'm going to give you some examples of that. So counting emails received by time t. If this time is continuous, it's a Poisson process. Given our lambda, we would be able to figure out the distribution of, for example, xt. Again, our variable xt here is the stochastic variable that we keep track of. This t can maybe increasing all the time. So, and its distribution will be given by a Poisson variable with lambda t. In this case, the parameter. If t time passes, if the average number of occurrences is lambda per unit time, if t time passes, then xt will be the distribution of xt. So the state distribution of xt will be a Poisson variable with lambda t. So by fixing time at time t, we will just be doing the exact same analysis we did. And the time that passes between two states, for example, if you have counted 4 buses, what is the time that is needed until the 5th bus arrives? What is that expected time between 2 events? We are going to see that as exponential. If we do the math, we will get exactly the same as exponential distributions here. So therefore, geometric distribution is just the discrete version of exponential distribution. We already knew these things actually when we talked about them in chapter 3 and 4. So this is just this section 6.3 is again relating all of them together in a continuous time process. I mean, when I say continuous, it may be discrete time, but as the time ticks away, if we continue doing this analysis for a prolonged period of time, not for a fixed time point, if we keep monitoring the time and looking at how this variable x behaves, all these relationships between these distributions again become more clear. So both of these examples are Poisson processes because the time t here is continuous. By time t, if the time itself is like trials, a binomial process. Each time step actually contains a Bernoulli trial. At every time step, we are doing a Bernoulli trial. If it's like that, it becomes the discrete time, and it's called the binomial process. Xt is the number of successes by time t in a sequence of independent Bernoulli trials, and therefore this is exactly what I have written in the previous slide with the annotation. Xt becomes the number of successes by time t, and it's simply its distribution is given by a binomial t times p. So the binomial tp is it gives us the probability mass function of this, gives us the the state distribution of xt at time t, of x at time t. And the number of trials between two successes, if we call them the variable y, so it's basically how many tries you need from one state to another state to transition from the next state. It becomes a geometric variable with parameter p, its success probability p. One thing that we need to be clear here is that sometimes this t is given to us again in terms of minutes or seconds. In that case, we may be thinking about, for example, we are doing a one Bernoulli trial every 3 minutes, okay? When we are doing something, let me again write it here as annotation. For example, if we do a single Bernoulli trial every 3 minutes, okay, and we ask something about what is x9, where this t shows t in minutes. We need to be careful here. The xt here, x9 here, is not equal to 9 times p, because in 9 minutes we don't do 9 trials. If this t is given to you like this, you need whatever your delta time is. So if this delta, which is sometimes called the frame length, each frame is 3 minutes long, okay? And in every frame you are doing some trial. In that case, your binomial variable should be t divided by delta times p, okay? Because in 9 minutes, we don't do 9 trials. If our frame length is 3 minutes, we do a Bernoulli trial every 3 minutes, then the number of trials that we do in 9 minutes will simply be found by dividing this t by our frame length. This is the number of frames exactly we have in 9 minutes, and that becomes your binomial variable with this binomial tp is t becomes t divided by delta. So if you do at every time step you do one Bernoulli trial, in that case your delta becomes 1 anyway, okay? In every minute, for example, every 1 minute you do some Bernoulli trial. So the t that passes in minutes directly corresponds to, therefore, the number of trials. Therefore, this one, t divided by delta, is going to be t anyway. So this is how we can do. But you need to be careful. If delta is given to you as like a certain amount of time and your unit of time is minutes, and if you try to monitor your stochastic variable again in minutes, not in number of tries, if this 9 that is given to you inside it is minutes, then you should do t divided by delta. And if what happens if this time is not a multiple of 3, for example, this will be interesting actually. It may be, you may do either an integer division. In 10 minutes, I still do 3 trials, but in this time frame of delta, where you do the trial exactly is not specified. So is it at the end of every delta? If it's at the end of every delta, you assume that there's a trial, then it's this x10 could still be, you can still do divided by delta with integer division to say that I didn't, at 10 minutes, I haven't done yet the 4th trial yet. So I'm still at trial number 3. So you basically conduct an integer division to find the number of trials. But usually this will not happen. I mean, if you go into the domain of non-integer time units, then you basically go away from the discrete time binomial counting process, and you jump to the domain of a Poisson process where you show the time in a continuous manner. Okay, if we have the time steps in a like discrete as number of trials, we have what we have is called a binomial process. And here is a nice, as I said, this shows relates all these distributions nicely, visualized nicely in a single figure. So the time between two state transitions from state, for example, 3 to state 4, we see a geometric, the number of trials between until next success becomes a geometric variable. And this h, as you mentioned, Khan, it may be 1, 2, 3. So whatever this geometric variable, geometric p variable can take, it's the values it can take maybe from 1 to infinity. And it shows you that you may have to wait that many number of trials between two states. Delta here is the time in units, whatever units of time you have in unit time between two trials, that's delta. If you conduct a trial every 1 minute and your unit of time is minutes, then delta is going to be 1. All right. And here are xt variable, and here is a binomial. If at n trials, if the success probability is given to ESP, the value of xn, the state distribution of xn, is simply the binomial mp. Okay. Yeah, this is the same thing. I already mentioned this slide, number of trials versus time. If yeah, the example that is given here is this is like every 3 seconds. X6 does not become binomial 6p, but it becomes binomial 2p because in 6 seconds we just conduct 2 trials. Okay, so here we have to divide the t by the frame length if this delta is not 1 second, or if it's more seconds, and our unit of time is still seconds when we are monitoring this stochastic process. So we have to be careful about this issue. And when we talk about lambda, now we are going to take all these things like the success rate, the interval. So now we are going to jump to the Poisson process, where this delta is going to get smaller and smaller. Okay, in Poisson process, the time is continuous, so the number of trials, the delta is going to be infinitely small, but which also makes p infinitely small too. For example, if buses arrive every four buses arrive every hour, the probability to arrive a bus in the next second is going to be very small, right? If you go second by second, the probability to have a bus in a second is going to be very small if a bus arrives, 4 buses arrive every hour. So lambda is going to be a fixed 4, but the probability and this delta is if delta goes to 0, probability p also goes to 0, but their ratio remains fixed as lambda in Poisson processes. So, but even we haven't jumped to the Poisson process yet, but the arrival versus success rate, their relationship is if p is the success rate at delta units of time, then lambda becomes the success rate per 1 unit of time. So this lambda becomes p divided by this. Okay, for example, if this was your lambda, your delta was 1 minute, and if your success rate was 0.6, lambda is also 0.6, right? If it's 0.6 success rate every Bernoulli trial, and you do Bernoulli trial every minute, your lambda in minutes is still 0.6, because 0.6 in every trial, if every trial is every minute, it still means 0.6 on the average every minute. But as this one gets smaller, we will have, if delta gets smaller, we will have, for example, if the success rate is 0.6 every minute, If you reduce your minutes to 0.5, here this one reduces your lambda. And if your goal is what is the success rate every half minute or every 10 seconds, it's going to increase. But in that case, we are going to fix lambda, not we are not going to just change this and make lambda remain the same. So, and t becomes the time between two successes. We already shown that y was the geometric variable, but if your delta is not 1 unit of time, the time between intervals, if you measure time as in minutes, this geometric variable number of trials, expected number of trials times delta, your frame length, becomes the time you have to wait. Okay, so if you have to conduct, for example, 6 trials until next success, if every trial is like 3 seconds, you have to multiply 3 seconds with 6 trials to get the expected time in seconds you have to wait. So yeah, this is like a graph that you mentioned, Khan. So the counting process is like a graph. If you think about the state transitions, we start at 0. The counting process starts at 0. And the state transitions, as you can see, is always between itself. We may, in the next time step, we may stay in the same state or go to the next state. So going to the next state is exactly the success probability. If you have a success in your Bernoulli trial, you're going to increase your state count and you're going to jump from 0 to 1. So going to the next state has probability p like this, and remaining at the same state is 1 minus p of this. I already answered this question. Is it regular? It's not regular because when you are at state 2, the transition to state 0 is going to be all 0 in any h step probabilities from here. So in other words, we can write this nicely. P20 is always 0. It's impossible. In a counting process, going from state 2 to state 0 is impossible. It's always 0 for all h. Sorry. For all h, this is 0, which means that it's not regular. It's irregular. There's another nice figure in the book that shows the state one-step state transition probabilities. Let me show that to you quickly. There are some. Yeah, it's this. So the transition. Let me zoom in. The transition probabilities that I have shown you on a graph also shows in matrix form. It's like this. One thing that is interesting about these Markov chains is that this matrix has not a definite size. It has infinite rows and infinite columns because the counting process, as time continues to infinity, if you're monitoring this binomial process, you may the count you have may reach up to infinity in infinite time steps. But if you fix your maximum time steps to something, for example, I'm not going to monitor this process more than 1,000 trials, then you will have 1,000 by 1,000 matrix at most. All right. And the thing about Poisson process is that it's not here. It was here. When the frame length between two trials approaches 0, we don't have trials anymore. When we're counting buses, for example, we have 4 buses in an hour arriving in the station. Lambda is fixed, but the time unit that we measure things become the time frame approaches 0. If you think about trials, the probability of having a bus in every second. So what is the probability to have a bus at every second? It's a very small probability. So P also approaches 0 as this frame frame length approaches 0 when it becomes a continuous stochastic process. But as in a Poisson process, the arrival rate per unit of time is taken as constant. That's our parameter lambda. If this is given, when this lambda is given to us, we may still model continuous counting processes. Okay, and xt becomes a Poisson variable, lambda t. I mentioned this before. And the time between two events becomes an exponential variable with parameter lambda. And we can also relate the gamma distribution to this, the gamma Poisson formula. The Poisson problems could be solved using the gamma distribution in chapter 4. There was this equation 4.14 in chapter 4. It was the time needed. Remember, gamma is like a summation of exponential variables. So to go from state k to state k, actually, so for example, state 0 to state k. The probability to go to from state 0 to state k is this gamma k lambda variable. And the same thing, the gamma Poisson variable, the probability to have k successes before time t could be given as the gamma variable. So the waiting time for k to observe k next events becomes a gamma variable, and xt itself becomes a Poisson variable. So as I said, in this section, everything is related to each other in a time, in the time domain as well. And here's the visual figure that I wanted to show you. This is going to be the last thing that I want to show you from section 6.3. The same, it's very similar to the binomial process, but this time the time, these bar, the x-axis, the time that is spent to jump to the next state is continuous. So we have continuous time, but still it's discrete state. We are counting. As you can see, this axis, the y-axis, which shows the counting process xt itself, is discrete. We jump from 0 buses, 1 buses arrive, 2 buses, 3 buses, 4 buses, 5 buses, 6 buses, 7 buses. As time goes like this, we keep counting the buses. And at a specific, if you fix on this x-axis, if you want to fix time and take a look at what is this distribution of what is the probability of observing, for example, 8 buses. So this shows a specific realization path of xt. But if this graph shows what is observed. This is an example observation. If we have this observation and we are talking about things at state distributions, what will happen at time t, it becomes a Poisson variable with lambda times t. Because in t units of time, if the arrival rate is lambda units per unit of time, if t units of time passes, and if you're asking for how xt looks like in t units of time, it becomes a Poisson variable lambda t. Just like as we did to solve Poisson-related examples, like if somebody gives you the arrival rate every week, okay, it rains on the average 2 times a week. If we are asked a Poisson question, what is the probability to have more than 5 rainy days in 3 weeks? What do? We do model it with a Poisson 2 times 3. If it rains 2 times on the average per week, in 3 weeks, it rains 6 times per 3 weeks. And then it becomes a Poisson variable with lambda is equal to 6. And when we ask a problem, what is the probability that it's going to be larger than 5? We just look at the CDF of Poisson with lambda is equal to 6, and 1 minus CDF is going to give us that probability, right? So the variable itself becomes Poisson. That's why it's called the Poisson process. The waiting time between two consecutive states is an exponential variable, and the waiting time between multiple events, they become gamma. I mean, if you, for example, jumping from state 0 to state 5, the waiting time until the 5th bus arrives or 5th event is observed, the total waiting time until the 5th is observed become a gamma variable, okay, with state, name, and lambda. And the last section is just, I have one slide for that because it's very simple. Whatever we have learned in chapter 5 to simulate random variables. The simulation of stochastic processes is very simple. We just use the same random sampling techniques to sample from Bernoulli distribution, binomial distribution, geometric distribution. So those techniques we learned in chapter 5 are the same techniques are used to simulate stochastic processes. If state transitions are discrete with specific probability mass function, if you know the probability mass function, you know how to sample from a specific probability mass function, the algorithm 5.1 given in chapter 5. And I also stated this earlier, even the steady state distribution of a regular Markov chain can be found using simulation by iteratively jumping from state distribution to state distribution by multiplying the current state distribution with the one-step state transition probabilities, that 1 times n row matrix multiplied by that m by n one-step transition probabilities. You figure out what will happen in the next time step. If you continue doing this with simulation, after certain time points, you're going to see that 2 successive state distributions are going to be equal, or they're going to be very close. If somebody asks you, for example, find this until 6 digits after the decimal point, you may just, if these 2 state distributions are not distinguishable from each other after 6 decimal points, before 6 digits after the decimal point, you may deem them equal, and you may just consider that as your steady state distribution. So this is how you may simulate stochastic processes. All right, so this concludes everything, and we are like 15 minutes early. I will be happy to answer your questions about general, about any topic, and I will stop recording now.